perform its function. So we have two drugs. One of them is trimethoprim. Other one is a derivative of trimethoprim. I will call it DTMP. This is the new antibiotic. So in this project, we want to investigate which of the antibiotic is better by using some computational methods. So to understand how mutations affect this protein, actually, we need several initial structures. So for these initial structures, we do some molecular dynamic simulations. We perform 1 microsecond long molecular dynamic simulations for 3 forms. One of them is apoform, the DHFR without any substrate. And the other one is TMP bound form, and the other one is DTMP bound form. So to understand how conformational landscape changes, how the structure of protein changes, we perform some analysis. One of them is hydrogen bonds, other one is SASA, and the last one is clustering. So hydrogen bond is actually, this is the drug here. So between drug and the protein, there are some hydrogen bonds, and those hydrogen bonds are important for investigating the strength of binding, so also known as binding affinity, and I will also use the jargon of binding energy. So first thing is always to look at hydrogen bonds between the protein and the ligand. In here, you can see that, let me convert the laser pointer. So this is the upper form. This does not have any hydrogen bonds, but in here, this is one of the TMP bound and the DTMP bound forms. It has some hydrogen bonds. And as you can see, they change through the MD trajectory, which means that actually hydrogen bonds are not a static phenomena. So they change through the MD stimulation, and therefore they are dynamic. So actually assessing a drug binding by looking at the static structure only might be misleading, where actually we can see here. So as you see, the TMP bound form fluctuates between 1 hydrogen bonds, while the TMP form actually has some 2 hydrogen bonds and 3 hydrogen bonds through the MD trajectory. The other one is SASA. SASA is solvent accessible surface area. So you have your protein, and protein has a surface, and we want to calculate the area of that surface that interact with the water. Why it is important? Because proteins are always in soluble environment. It's an isotonic solution in our body, and proteins always wiggles and jiggles in that environment. Actually, they are really dynamic entities. So to understand how their interaction with the water changes, we calculate the SASA. Again, SASA is not something that is written in stone. As you can see here, actually it changed drastically for these 3 forms of DHFR. The last one is actually it's like a statistical method. It goes and calculates the RMSF in the structures and make clusters. Hence, there are these 3 clusters here, the yellow one, black one, and the purple one. As you can see here in TMP bound form, you can see 3 population of clusters that change through the time. And for DTMP, actually, there is nearly only 1 dominant structure here. And for the upper form, it also changes between the clusters. So by assessing these results, we select the initial structures to calculate the FEP simulations. So we perform mass FEP simulations on Carolina HPC facility. It's the Czech Republic supercomputer. We applied via Euro HPC project and get the computational time there. So we selected 33 positions why we go and check the literature. And there are some, we select 16 possible single mutations. So in a wild type amino acid, there are actually 19 possible amino acids there when you exclude the wild type amino acids. But with this method, you cannot do proline mutations because proline goes and connects to the backbone again. And the glycine is somehow very dynamic and very destructive in terms of energy. It's again uncalculable or maybe difficult to calculate via this method. And also, since there are 8 GPUs, we want to parallelize these simulations. We also omit one kinds of amino acid per position to further mutation scanning. The previously mentioned MD simulations, we take 3 duplicates. So we go and check those MD simulation and take 3 initial structures. Therefore, now it is 33 times 16 times 3, 1,500 something. And there are 3 forms, APO, TMP bound, and DTMP bound. So again, there's 3. So there's, on total, we will calculate 4,752 FEP simulations. So what is an FEP simulation? Actually, if you say this is our protein and we want to mutate it from here to there, so we will change this amino acid to that. First, we generate a hybrid amino acid that consists of wild types and mutated forms atoms. So, for example, let's say you want to mutate alanine to valine at this position. For that position, you put both atoms of alanine and valine. However, the alanine's atoms are energetically there, while valine's atoms energy equation are multiplied by 0, therefore making them just the balls. So you do not have the effects of the gonna be mutations atoms. So step by step, you increase the mutated atoms equations while decreasing the wild types atoms equations. At the end, you have multiply 0 for the wild types energy equations and 1 to mutated ones energy equation, having the only the mutated versions energies. Also, you do it backward to understand if this is reversible, because thermodynamically this process should be reversible if we want to assess this as a thermodynamic energy quantity which we want. And you check the energies if they are the same or not. So that is the reason the name alchemy comes here. Actually, through the way we do not use the real physical forms of the amino acids, but our initial and final forms are the approximates of the exact physical amino acids. So actually this method was an old method. It came in 19th. However, by using MD3, after 2020, it was possible to run this method on GPUs. And with the new coming GPUs, which are really strong, it was possible to do mass FEP simulations. Therefore, the method is old. However, using it in a high throughput manner is the new phenomena here. So we use Carolina nodes. Carolina nodes have 8 GPUs, these A100 GPUs, which are quite good. And they have processors. We use NAMD3 software and Charm 36 force field. So we parallelize our simulations. Actually, parallelization is a bit difficult. Why? Because for each FEP simulation, first you have to minimize your initial structure, then run the forward FEP simulation, then run the backward simulation. So you need to have 8 parallel process, which contains 3 sequential processes. So this is actually published in this paper. We explained really in depth what we did on Carolina computer actually in that paper. So first thing is actually to do the benchmark. We want to understand how much time do we need to run our simulations, because for each system, for each initial structure, simulation time is different. Why? Because you have a different initial conformation. That conformation has different number of contacts. So with the different number of contacts, you need different computational time. Why? Because you have more number of energetic things between the atoms. So in an actually force field, you need to calculate van der Waals energies, Coulomb forces for the unbounded interactions. Therefore, if you have different conformations, actually your number of equations, hence your number of your need of computational time differs. Here, as you can see, we have these probability distributions. This is the mutations to neutral to positive amino acids, neutral to negative, neutral to neutral. As you see, actually, they are different in every kind of amino acid mutations. So after running the FEP simulations, we will have our mutation energies, because for each forward and backward FEP simulations, we will have a mutational energies. The mutation energies gives what is the energetic cost of this of inserting this mutation there. Most of the energies are on the positive side. Again, this is the neutral to neutral, neutral to negative, etc. So the diagonal is for the same kind mutations, and off diagonals are for the different kinds. So if the energy is negative, it means that the inserted mutation is more favorable compared to the wild type. If it is positive, it means that by the insertion of the mutation, we disrupt the energetic state of the protein, hence the energy is positive. As you see here, in the neutral to neutral, we have some negative energies and the positive energies. And for the negative to negative, the change is nearly minimal. And positive to positive, also the change is minimal. However, for the others, especially from the negative to positive, all the mutations are disruptive. So there are these energies, but do we know that if these energies are trustworthy, so our calculations are correct? So the one thing is they check the variances. So in an 310 Kelvin environment, the temporal fluctuations leads to energy change about 0.7 kcal per mole. So let's say that in a 1.5 RT, we expect 1 kcal per mole energy in the environment. Hence, it means that we cannot calculate energetic changes lower than 1 kcal per mole. And also, it gives us a measure to understand if our simulations are correct. So we want our variances to be lower than 1 kcal per mole, because it means that it lays within the natural error of the temporal thermal fluctuations, which means that we do not have any additive accumulation of errors in our calculations, leading that our calculations are correct and trustworthy. So when we look at our simulations again, these are the variances. As you see, from neutral to neutral, all of them are below 1 kcal per mole. And when we change the sign from negative to positive, actually we have some higher than 1.5 kcal per mole variances here. And again, for the same kinds, actually it's minimal. And when we try to change the sign, we have some higher variances. So this means that our simulations are correct and trustworthy and in minimal in terms of accumulated error of energies. Oops. Yes, sorry. So we have our mutation energies, and we will have some ligands. And how can we convert these mutational energies to binding energies? Because we want to calculate actually the binding energies. So there's a thing called thermodynamic cycle. So in a thermodynamic cycle, we will start from the apoform and the non-mutated form. And when we mutate our structure, we will have this form, right? And also from here to there, we will have our binding energy, right? Again, when we start from the apo non-mutated form, we will have this binding energies here, because you see, this is the ligand, this is the protein, and it binds to that hypothetical violin. And again, it's mutated. So in FEP, we don't calculate the mutation energies, but the experimental energies, they calculate only the binding. So at the sites, these red marks, they're experimental energies. In experimental energies, people give you dissociation constant. So by using the inverse Boltzmann, you can convert this dissociation constant, KDs, to binding energies actually. Minus RT, RT is the gas constant, this is the temperature, this is Ln, this is the dissociation constant. So sometimes it shouldn't be, the probability is enough to calculate some energies. So in some new mutational scanning experiments, people also put survival there. So compared to the wild type, people use the survivability of the mutation. So you can actually put survivability here to as a measure of binding when you hypothesize that binding is essential for its organism to reproduce. Therefore, it is based on your hypothesis. So it does not have to be a experimental binding energy. So we have two experimental energies, and those are the ones. This is the wild type of ligand binding here. This is the mutant ligand binding here. When we subtract this one and this one, like here, we calculate the double delta GA. So what does it tell us? Actually, double delta GA gives us if the mutation or the wild type binds to this ligand more favorably or not. As you see here, if this is more negative and this is less negative, the result will be negative. Therefore, it shows that the mutated structure binds to ligand more favorably. If double delta GA is positive, it means that your wild type binds to ligand 1 more favorably. So by assessing the sign of energies, and it's actually the magnitude is also important. So the changes, like as I told you, 1 kcal per mole is insignificant actually within the error bars. However, the changes in a few kcal per mole, 3 or more, might be more significant in this sense. And we can calculate also the mutation energies. You see, these are the arrows of computational mutational energies where we calculate by FEP. So we take three structures from MD simulation. We can calculate the average of three FEP simulations. As you see here, this one and this one. So when we subtract this and this, we can calculate the double delta GA. Again, if this is negative, it means that mutated and ligand bound structure is more favorable. If it's positive, the mutated and non-bound structure is more favorable. Hence, again, giving the same information upon ligand binding if mutation is favorable or not. Therefore, we can actually equalize those two energies, double delta GA, and have our relative binding energies. Actually, we can also increase it to one step further. So we can calculate the same mutation with different ligand and take the energy, the delta energies here, which means that upon which ligand binding, this mutation is more favorable. So you have this mutation and you want to inhibit that mutation. You construct a thermodynamic cycle like this. So you subtract double delta G and double delta GA, and this result gives you a negative energy to you. It means that for this mutation, the blue drug is more effective. Actually, if you have any questions, you can cut me and ask. So yes, this is actually triple delta G is used to confirm our computational results against the experimental energies. So if this is actually, this is what's open, I will go with the relative binding energies and variances. So for DHFR, we find that this is our heat map. So by calculating the energy differences, we can check which of the drug is more favorable. So blues prefer the derivative of the new antibiotic, and the reds prefer TMP, the old antibiotic. We find that 26 of 33 positions favored the new antibiotic. As you see, the energy differences range between 4 kcal per mole, which makes this significant. And also, while the when we perturb this position with the mutations, the preferences always go for DTMP. But there are some mixed behavior. You see, with this mutation, this protein become more sensitive to DTMP, and with this specific mutation, it becomes sensitive to TMP. We have also mixed behavior for other positions. As you see, this is not as simple as it looks. Therefore, the protein is a complex entity. Hence, each mutation may give results differently. So it changes the conformation of the protein, leading a different mechanism of action. Hence, the emergent behavior is different, making it to show complex behavior in terms of mutations. We are still actually in the process of calculating the experimental results of this project. Therefore, we have the experimental results, but haven't calculated them. So in the future, actually in a couple of months, we will calculate them and hopefully publish it. And also with the relative binding energies, there are variances, and when you subtract then some energies, the error accumulates. Even within the accumulated sense, we want our energies, the variances of energies, to be lower than 1 kcal per mole. So we take the relative binding energies here. As you see, this is the 1 kcal per mole. Most of them are lower than 1 kcal per mole, making actually our relative binding energy is really reliable. And at the end, we can say that newly developed drug targets DHFR mutations well and slows the antibiotic resistance. And actually, this is the end of my talk. So I want to thank you. This is our MITS lab. This is Canan Atılgan and Adirana Atılgan. And I led this project for the running of high throughput FEPs. Bushra ran the MD simulations, and our new PhD student Kübra is also running the simulations. So these simulations are performed on the Carolina cluster via this project, and we are still actually running the new positions and actually the higher number of mutations. So for this project, we only ran the single mutations, but we can actually run the double mutations and triple mutations. On Barcelona supercomputer Mare Nostrum 5, as a group, we are still running the large number of single mutations and the extra double and triple mutations. This research is supported by NIH grant. This is our website, and this is the GitHub of our lab. On the GitHub, the codes to run these high throughput FEP simulations are open. Also on this paper, it's explained, therefore it's easy to use. This is my website. I put codes and GitHubs and explanations with the schematics on my website. Also, you can go and check it. And also there is this, I'm a member of EuroCC4C project. And in that project, there is this Turbas open lecture platform. On that open lecture platform, actually, I will create a lecture of these FEP simulations. There is one lecture, there are lots of nice lectures on there, but one lecture of MD simulations of small molecules there, I gave that lecture and recorded it. And for in the next few months, I will also put the FEP simulations in a really simple manner where I give the codes and etc. So I suggest you to follow that website also. So thank you.
Thank you so much. This was really amazing. Thank you. There are some questions, but maybe I can go first. First of all, my question is this, I want to start with this. What was the third amino acid that you omitted? You said proline, glycine, and the one another?
So the other one is actually from the literature. So we don't have a specific amino acid kind. For each position, we look at the literature and omit the least important one. Let's say that if there is this, the position was a positively charged amino acid, we don't want to mutate it both alanine to valine. We skipped valine in that case. The reason we do is for the operational issues, actually.
Okay, so if I start for my system, I also need to omit one of them because
no, because for on the Carolina supercomputer there were 8 GPUs for each node. So we want to parallelize 8 GPUs, and actually let me just go. Yes, this slide. So there's these 8 GPUs there. We want to so there's these 2 nodes, and which makes them 16 GPUs. On that 16 GPUs, we can run 16 FEP simulations parallelized. So if we don't want to waste the computer time, because these computers are like when you cannot reserve one GPU. So you can use the whole computer one time. So you cannot go and run one FEP simulation because it will be a waste of computer time. Hence, we omit one amino acid, make our mutants are 16 amino acids, and run that simulation. So if you have a at-home computer or where you can use a local computer, you can actually run 17 FEP simulations really easily. This was for operational issues.
Okay, thank you. And my second one is this. When you show the like the energies, I think it's like the previous one maybe. No, the previous one. Okay. No, the previous one. Sorry.
This
So,
one,
as far as I see that the positive to neutral was much more changing the your structure than the negative to neutral, right? So, is this because your drug is targeting the positively charged?
so good question. So in here, this is actually the whole system's energy. Therefore, each position might behave differently. So this was just the benchmarking reasons that we put negative to neutral, positive to negative. Of course, the sign changing mutations are disruptive to the system. Let's say that you have a protein like this. These two regions should attract each other to have a favorable state of conformation. When you change this mutant to positive, those two positive amino acids will repulse each other, therefore leading a change in conformation drastically, leading a high energy change. So in here, these negative to positive and positive to neutral mutations are more pronounced because they change the structure drastically. So in here, we cannot do that. The drug has an effect on these conformational changes. It might, but this is the energies where we take account of all structure and the system, actually, even the waters. So therefore, we can generally say that this mutation disrupts the whole conformation of this protein.
Okay, thank you so much. There are like I have to go with other people's questions. So do you want me to read it, or are you gonna maybe I can read it, or if the people who
Actually,
ask
I
it
can also read it.
Okay.
So, what is FEP? Why do we do MD simulations 3 times? So the last question is the easiest one. Are there experimental studies that confirm these results? Not yet. We have our collaborators in UT Southwestern's Erdal Toprak. He gave the experimental results, but I haven't analyzed them yet. I will. So what is FEP? FEP is free energy perturbation simulation. This is the method's name because you actually perturb the amino acids. That's the reason it is free energy perturbation. Why do we do MD simulations 3 times? We didn't do MD simulations 3 times. Actually, 1 MD simulations for each form. But we did FEP simulations 3 times with different initial structures because this is the initial structures are important. So you want to actually sample as different as conformations possible. So therefore, you want some different initial structures. So we go and in here actually, so these are the MDs. We go and take 3 snapshots from MD simulations to cover the most area, most different conformations here. Statistically, the best thing is as much as you can do. However, there is computational resources are not infinite. Therefore, we need to do as little as possible. But in our experiences, we know that the 3 is enough for the different, like there are some really interesting positions when you change these mutations, the conformation change drastically. You cannot have a stable result. You can also increase the number of FEP simulations to 5, 7, etc. However, 3 is enough in terms of our experience. Thanks for how much accuracy different between this approach. Yes, actually, So how much is the accuracy difference between this approach and wide use approaches like FoldX? Is it scalable to large proteins? Actually, compared to FoldX, uh, this is way better because in FoldX, there are these fitted uh, force fields. They try to fit their energy equations to experimental findings. Hence, it's actually erroneous because the sample changes all the time and they need to come up with new models all the time, and it's not feasible. Actually, we also did it for another protein, and FoldX was not that successful. This FEP is the actually best tool nowadays. However, it is highly computationally expensive. That is the reason computationally expensive, difficult to run because if your initial structures are not stable, it will not work. Or through the process, if there are some energetic fluctuations, errors, it will not work. So you need to set your parameters. So there is these, you see, I increased the increase the equations of the mutation and decrease the wild type. There are some steps on that sense. We did it in 32 steps, and some of the system you might need to increase it to 64 steps. And also you need to tune your equilibration process based on your system. Therefore, this is the best method. This is the actually method that approaches to the experimental in the literature also. However, it is computationally expensive. Is it scalable to large proteins? Yes, but again, you need to have a supercomputer. Actually, also from Turkey, people try to apply for Euro HPC projects. Hence, applying a Euro HPC project might be feasible. There is this another question. On the heat map colored like blood, I understood each change amino acid and its position made the protein more sensitive to wild type or mutated. Okay. Why are, yes, here. Oops. So why are some are black or gray? So grays are the wild types. We don't mutate wild type to wild type, and the black ones are the ones that we are omitted for the sake of operational purposes. You will not see glycine and proline there. We skip those rows entirely. However, for each position, we also skipped another mutation. Therefore, we mark them with black.
Do we have any further questions? Thank you so much. Really, this was really a very good talk. Thank you.
Thank you. Also, feel free to send me an email if you have any questions. I write emails answer emails really quick. If I don't have time to answer them long, I tell them only saying that I will answer it in 2 days, 3 days. So feel free to write an email to me. Another question, I think. Yes, thank you. You're welcome. Other than that, if you have any questions, I can answer. Yes. Thank you.
Okay, last call for the questions. Maybe you can answer like in a general for, I know that this is system specific, but for the protein that you showed here, what was the residue numbers for your protein here?
159.
Okay. For that kind of system, what was the whole computational time for the whole process? Approximately.
approximately, let's say that we did three position. Actually, running this on supercomputer is not that long. It took 1 month, but the whole process. So in here there are also lots of side files. So you upload thousands of 5,000 files, let's say, and you download 20,000 files. So downloading them, checking them, they are the ones and also take some time. So we try to also tune our files. So this project took 1 year, and we finished it exactly in 1 year. So it's not that we ran it in 2 months and wait for the result. No, it really took 1 year. So because at first we were not used to do this thing in a high throughput manner. When you try to run this thing in a high throughput manner, you need to also do some hypotheses on how you run the simulation. So for the initial structures, we were discussing like, should we put an additional equilibration MD simulation for each mutation? So when you put an equilibration MD, actually you do not know if the last frame will be favorable or not. So you need to check your simulation. Hence, I tell them that we cannot do it. We can only do the minimizations so that we will be sure about the last frame will be energetically stable. Therefore, we did those actually hypotheses. And again, the code should be written in terms of this Carolina GPU. We converted to the Barcelona supercomputer, and we needed to change the codes actually. In here, we use, let me show. So write 16 CPUs per one GPU. This was A100. And we find that actually in Barcelona, there's these newest GPUs. It's called H100. For H100, for this system, when you increase the number of CPUs, you slow down the simulation. So actually, one CPU works well because at the end, I think the GPU, when your GPUs are strong enough, the number of CPUs have a bottleneck effect on the AMD simulations. Therefore, we had these kind of problems on while running this simulation. I think I see one question. How did you mutate amino acids in MD? We can't generate or break bonds MD. Did you mutate the amino acids in FEP? Yes, we mutate amino acids in FEP. Actually, in here, so yes, you can't generate or break bonds in MD simulations. However, you can in FEP simulations. So we start from the hybrid amino acids, actually, which have the atoms and bonds for wild type and mutation, and we tune their equations. Therefore, yes, we somehow tune the energies of bonded and non-bonded energies in FEP simulation. Any other question? Okay, now I'm stop sharing. Yes, one. Thank you. Okay, I'm stop sharing.
Thank you so much. And if you can send me the link when you give the lecture about it in the Truba, I guess, right? Ulakbim? I don't know. I can share it with the whole group in the
Okay. Okay, so let me copy and paste that to the chat. Oops, I couldn't do it. Okay.
And I will also put the your GitHub. So Thank you so much. I can find it. I can find your GitHub. Thank you so much
Okay.
for your time. And then like this was really a good presentation. I think I learned a lot. I'm sure that people also learn a lot. Thanks for answering all of our questions and making time today.
Thank you very much.
Is there anything
Okay.
that anybody wants to say before I end the meeting? Okay. Thank you so much.
Thank you. Bye bye.
Bye bye.